Our next topic of study is the outer solar system. We've talked about the inner solar system, Mercury, Venus, Earth, Mars. Now I want to talk about the outer solar system. In the earliest days of space exploration, we were able to send spacecraft to the moon and to Venus, which is our nearest neighbor other than the moon, and to Mars. For much of the time, we were mainly sending spacecraft to Venus and Mars and the moon. That held true throughout the 1960s. And so problem is getting to the outer solar system is very hard. It is much farther away. You have to be changing the orbit of your spacecraft very much more than to get to a nearby planet. Even getting to Mercury turned out to be kind of difficult because we had to slow down the spacecraft to fall that close to the sun. You had to really speed it up to get to the outer solar system. And so this became kind of a problematic study. Astronomers and engineers and scientists believed that we could get to Jupiter, but we didn't really have a rocket big enough to get past Jupiter. So what do? Well, interesting thing, astronomers realized that in the 1970s, the outer planets would be lined up in such a way that if you go to Jupiter and pass behind Jupiter, Jupiter's gravity would pull on the spacecraft and speed it up and sling it on to Saturn. And you got to do it just right because Jupiter goes around the sun once every 12 years. Saturn goes around once every 29.5 years. So only every now and then are they lined up just right so you could go from one to the other. But that happens, every dozen years or so, and that was actually happening. And the other thing is that they realized that Saturn was going to be, and Uranus and Neptune to be lined up in such a way that Saturn could then toss you to Uranus, and Uranus could then toss you to Neptune. And so one spacecraft could actually visit all of those. So NASA proposed a space mission called the Grand Tour. And the idea was this was going to be the best spacecraft that we could build. It was going to be a very large spacecraft, very expensive spacecraft with the best instruments on board and the best equipment that we could possibly put, because this is a one-time deal. These planets would not be lined up in such a way that one spacecraft could visit all four of them for another few hundred years. And so this was going to be a very special sort of thing for us. And so if they didn't do it in the 70s, they weren't going to do it. And they'd have to figure out some way of sending, 4 separate spacecraft. All of them would have to go by Jupiter, and Jupiter's gravity could toss one to Saturn and one to Uranus and one to Neptune. Pluto was not in the mix here. We knew about Pluto at the time, but Pluto was not lined up in such a way that one of these spacecraft could really go by Pluto too. So we could get all the major planets. And so the Grand Tour was proposed. NASA started working on it. And so instead, they said, well, we've got these Mariner spacecraft. They're not the top-of-the-line spacecraft that we had hoped for, but the Mariners were very good spacecraft. We had Mariners been going to Venus and to Mars. We had just sent Mariner 10 planned to go to Mercury. So the plan was to have 2 more Mariner spacecraft, Mariner 11 and Mariner 12, and they would be launched as a pair, and they would be slung out past the other planets. Well, the idea was to send 2 of them, because if we sent 2, if one didn't work, the other might work. And so, but then they realized that these 2 spacecraft would just keep going, and they would actually be going off into interstellar space. The first things leaving the solar system. And so they said, well, we don't want to just, say, gosh, we are going to be sending these things out here and just call them Mariners. So they renamed them Voyager. So Voyager 1 and Voyager 2. But basically the Voyager spacecraft were Mariner spacecraft. The big difference was how they generate electricity, because the mariners typically use solar panels, and they realized that these things would be going so far from the sun that solar panels would not work. So they had to come up with some other way of making electricity for them. But other than that, the basic spacecraft framework was souped up Mariner. After they made the decision and they launched them, they were going to both go by the other planets, and along the way, things started, working really well for them, and they realized that they were going to sacrifice one of these. Voyager 1 was going to go from Jupiter to Saturn, and was going to be sacrificed at that point and take a path that allowed it to study Saturn's rings. And Voyager 2 would be the one that Saturn tossed onto Uranus, and Uranus would toss it onto Neptune. And so that became the change in plans. Now, the problem is that in order to get to the outer solar system, we have to go through the asteroid belt. And nobody knew what the asteroid belt was like. This image here shows all those asteroids between the inner solar system and Jupiter. And this is not at all the way it's like. We had talked about this before. I already told you that the asteroid belt is really thin, but when you think asteroid belt, even astronomers, when they were thinking asteroid belt, they were thinking that there might be a whole bunch of little small things out there too, meteorites and meteoroids flying around all over the place, and so the asteroid belt might be so chock full of stuff that no spacecraft could make it through unscathed. And no one had ever sent anything out that far. And that was a brand new issue for them. Secondly, no spacecraft had been that far from Earth before. And so when spacecraft went to Mars or they went to Venus, that was really only a couple AU away. And so they could send signals back. We had radio telescopes or radio receivers that could pick it up. They had to build special deep space radio receivers, basically radio telescopes dedicated to communication purposes to pick up signals from this far away. So NASA built what they call the Deep Space Network of radio telescopes spaced out around the world that were designed to pick up signals from our spacecraft that we were sending out beyond the nearby parts of the solar system. The idea that Jupiter could sling these things around was also something that was at the time untried. About the time that they were planning on this whole thing, this is when they would try the first slingshot of Venus to Mercury, but going from Earth to Jupiter and let Jupiter go on to the outer planets, they're so far apart that a small error could make a huge difference, and then you can end up missing it. And so they didn't want to risk their Voyagers, which, they were souped up mariners, but they were still way better than anything else that we had available, and they didn't want to risk losing these better spacecraft. So what they did was they launched two very rudimentary spacecraft, Pioneers. Now, the Pioneer series of spacecraft had, since the early days of space exploration, some of the very first ones that we launched were called Explorers, and then the Pioneer sequence were a whole bunch of spacecraft launched to new places, doing new things, basically testing new technologies. And so the first two things that we launched were going to be Pioneers, and they would fly through the asteroid belt and see if we could actually do that. Then they would fly past Jupiter and see if we could actually send signals back from that far, and let Jupiter toss them on to Saturn to see if we could actually do that too. And so then we would launch the Voyagers. All of these spacecraft, all the spacecraft going out that far from the sun have an issue, and that is the sun is not very bright. If you go twice as far away, the sun is 4 times dimmer. Well, at Jupiter, it's 5 times farther away from the sun than Earth, and so the sun is 25 times dimmer. At Saturn, you're 10 times farther away from the sun than Earth, and so the sun is 100 times dimmer. And so that means that we need some other way of powering instead of solar panels. And what they came up with is something called the radioisotope thermoelectric generator, or radiothermal generator, often is how it's abbreviated, or just RTG. The way this works is you have a chunk of plutonium, and plutonium is a very energetic radioactive material. It decays readily, and as it decays, it releases energy. That actually provides warmth, heat. And then you put a semiconductor in there called a thermocouple, which is actually two semiconductors meshed together. And that heat actually pushes electrons from one to the other, and that provides you electrical power. And so as long as this thing is warm enough to provide some heat, it provides electrical power. Well, the longer the plutonium is there, the less of it is there, because the heat is produced when it decays. And so the few less of it that's there, the less heat is being produced. And so as time passes, the radiothermal generator produces less and less electricity. The RTGs of the Pioneers were not that sophisticated, and so the Pioneers lasted long enough to prove the technology, then they died. The RTGs on the Voyagers are actually still providing a tiny bit of power to keep a few of the instruments operational, just barely. So that gives you an idea as to how well these work, because the Voyagers were launched a long time ago. So we'll talk about the Pioneers and Voyagers next.